Good evening to all. This video represents the summary for digital system design for this week. What are the topics discussed for this week? Boolean, algebra, and simplifications of Boolean function, minimization of Boolean function by using Boolean algebra and K-map. Boolean algebra is an algebra for logic. Mainly it is used to perform the logical operations in digital computer. In digital computer, true represents by 1 high volt and false represents by 0 low volt. So logical operations are mainly performed by using logical operators. The fundamental logical operators and are not negation. So AND operator, it performs logical multiplication and denoted by dot x y x dot y. Okay. OR operator, it performs logical addition x y x plus y. NOT operator, it's a negation. 0 can be 1, 1 can be formed to the 0. So truth table is mainly show the relation between the input and output, the number of possible combinations. If you having two input variable, the possible combination 2 power n. So that is a 4 combination 0 0 0 1 1 0 1 1. In Boolean algebra is mainly applied in computers electronic circuits. That circuits perform Boolean operations and they are called logical circuits or logical gates. So particularly in Boolean algebra, so we are basic logic gates well known: AND gate, OR gate, NOT gate. So AND gate is an so particularly these are the basic logic gates we are already discussed in the first week. Okay, input A, input B, output is equal to A or B, NOT gate. But here in Boolean algebra, there is some basic theorem of Boolean algebra. So what are the properties of 0? In Boolean algebra, 0 plus A 0 dot A is equal to 0. Then properties of 1 plus A is equal to 1 dot A is equal to A. Then commutative law, A plus B is equal to B plus A dot B is equal to B dot A. So here you see that A plus B is equal to B plus A. This another one comes from the duality. So duality means plus can be replaced to dot and dot can be replaced to plus. In case value 0 can becomes 1, 1 becomes 0. So in associative law, A plus B plus C is equal to A plus B plus C. This parenthesis will be different. So both are in left hand side is equal to the right hand side. So particularly in commutative law, only two input variables A, B. But associative law, three variables A, B, C. So this is one type of addition, this is dot. Then associative law, A, B, C is equal to A dot B, C. So parenthesis will be changed. So both are same. But here Boolean algebra so that left hand side is equal to the right hand side always. Okay, in distributive law, A dot B plus C is equal to AB plus AC. A plus BC is equal to A plus B into A plus C. Then idempotence law, identity law, A plus A is equal to A for Boolean algebra. A dot A is equal to A. In absorption or reduction law, A plus AB is equal to A dot A plus B is equal to A. That is duality. Complementary law, x plus x dash is equal to 1, x dot x dash is equal to 0. Involution law, x double dash is equal to x, and then De Morgan's theorem, x plus y whole bar is equal to x bar dot y bar, x dot y whole bar is equal to x dash plus y dash. So particularly De Morgan's theorem mainly proves that if A dot B is equal to A bar plus B bar, that is A dot B whole bar is 2 input NAND gate. So that is equivalent to bubbled OR gate. So what is bubbled OR gate means? See that in this symbol for NAND gate, A, B is the input. This is the symbol for inverter. Y is equal to A dot B whole bar. It is equivalent to implementation with the help of basic logic gates. So we are getting a bar plus b bar. So a bar we are using some one NOT gate, b using one NOT gate. So a bar plus b bar equivalent to, so that is in this bubbled NAND gate is equivalent to bubbled OR gate. This is a symbol for bubbled OR gate. NAND gate is equivalent to the bubbled OR gate. De Morgan's theorem. So that will be, remember always. Next theorem is again the same, a dot b whole bar is equal to a bar plus b bar. Another theorem is NOR gate. A plus b whole bar is a simply NOR operation. NOR is equivalent to the bubbled AND gate. So this is also prove that basic logic gate structure for your NOR gate. Against NOR is equivalent to the bubbled AND gate. This is a symbol for bubbled AND. Here A is apply the input. Inverted we get a bar dot b bar. That is A inverted a bar, B is inverted b bar, Y is equal to a bar dot b bar, bubbled AND gate. So that's then Boolean's theorem. So simplifications can be using any Boolean function can be simplified by using Boolean theorem concept to simplify reducing that Boolean function. Another method we are using K-map, Karnaug's map method. So this is also, so you always remember some Boolean's theorem. What are the theorem concept? So Boolean's theorem, you verification also same will be done in the corresponding inbuilt lab classes. So in built lab classes, only the verifications of Boolean theorems will be comes taken the example for this Boolean theorem. Let us commutative law verification, associative law verification, distributive law verification, and also for De Morgan's theorem verification. So simplify. So mainly in Boolean algebra. So Boolean algebra, simplify the Boolean function. You are applying some Boolean theorem concept. Finally, another one. So you are in order to minimize the logic function or Boolean functions, we are using one type is Boolean algebra. That is Boolean theorem we are using, or we are using K-map. So methods to minimize a Boolean expression is by using laws of Boolean algebra or by using K-map, also called as Karnaug's map. So K-map. So mainly this type of, so Boolean algebra, you draw the implementation using some basic logic gates or logic operators. Let us take some example in Boolean algebra. A plus b dot c is equal to a plus b dot a plus c. So this will be in according to the Boolean theorem proof. Implementations, you see that once again the distributive law. So a dot b plus c is equal to a dot b plus c. How to implement this type of distributive law? So first you see in left hand side a dot b plus c, here one OR operation, here one dot operation. So implementation by using some basic logical operators. So one OR gate and one AND gate is will be taken for this implementation. But in right hand side, a dot b one AND operation and a dot c another AND operation. In the both AND operation will be added plus, so one OR operation. So this can be implemented with the help of the logic gates. Why we are going for the K-map? In order to simplifications of Boolean function, you simplify the Boolean function in less number of terms or less number of simplify, the large number of gates will be reduced. So that's main concept for applying for the K-map. So methods to minimize Boolean expression by using laws of Boolean algebra or by using Karnaug's map method or K-map. So it is a graphical method used to obtain the most simplified form. An expression is a standard form, sum of product or product of sum. Okay. The simplest form of an expression is the one that has the minimum number of terms with the least number of literals. It is also called variables in each term. So finally what's concluded for with the help of the Boolean algebra or K-map comparing to minimize the Boolean function using the Boolean algebra, there is some difficult. So we are expression minimum number of terms in the Boolean expression, we are using the least number of variable in each term. Then we are simplifying the expression uses the minimum number of terms. We ensure that the function will be implemented with the minimum number of gates. So that's the main points to always you remember. Minimum number of terms, we are using the functions will be implemented with the minimum number of gates. By simplifying an expression to the one least number of variables or least number of literals, the function will be implemented with the gates that having the minimum number of inputs. Okay, so this is some example for K-map. So in K-map is a table methods. We are using a 2 variable K-map, 3 variable K-map, 4 variable K-map for simplify the Boolean function. So before that, we are always remembered for sum of product or product of sum, and also canonical form for sum of product or sum of minterms, and canonical form for product of maxterms, minterms and maxterms. So here see that in case for Boolean functions can be if f is equal to sigma summation of 0, 4, then in K-map method you just simplify this a b c 0 1 0 0 0 1 1 0 1 1, some rules followed by the K-map method. Then simplification, after simplification, that functions f is equal to, its answer is b bar dot c bar. So 2 variable K-map will be 4 squares, 4 tables, 4 squares, 4 minterms are possible. In 3 variable K-map 8 minterms, and 16 variable K-map, it may be, that is 16 square can be used for the 4 variable K-map. So 2 variable 4 square, 4 boxes, 4 minterms, 3 variable 8 square, 8 minterms, 4 variable 16 square, 16 minterms are in K-map simplification. So K-map simplification rules, you see that to minimize the given Boolean function, we draw a K-map according to the number of variable it contains. In case how to draw a K-map, number of variables. In case 2 variables, we draw that 4 minterms K-map. In case 3 variable, that is 3 variable K-map you draw. In case 4 variable, you draw the 4 variable K-map. So variable, let us some example. Only the function input a comma b, 2 variable is enough. In case input a comma b comma c variables, you are choosing 3 variable K-map, or in case input is 4 variable, you are taking the 4 variable K-map. Then we fill the K-map with zeros and ones according to its function. Then we minimize the function in accordance with the following rules. So this, in order to simplifications of Boolean function by using K-map. So minimize the Boolean function, your 2 methods will be followed, one for Boolean algebra, Boolean theorem concept, another one for K-map. So K-map we minimize the function in accordance with some following rules. So you always remember that rules. So we can either group zeros with zeros or ones with ones, but we cannot group zeros and ones together. So that is rule 1 for the K-map. Either group zeros with zeros or ones with ones, but we cannot group zeros and ones together. Okay. Then x represents sometime in K-map. There is x represent there, don't care, can be grouped with zeros as well as ones. So that's the rule 1 for K-map simplification. Then rule 2, group may overlap each other. Then rule 3, we can only create a group whose number of cells can be represented the power of 2. In other words, a group can only contain 2 power n, that is 2 power. 2 power 0 is 1, 2 square 2 square is 4, 2 power 1 is 2, 2 cube is 8, 2 power 4 is 16, and so on number of cells. So in case grouping, this is, you say some examples, this is the correct grouping. So 1 2 3, it's a 3 variable K map structure, 1 1 1. So this is one grouping. 4, this is one grouping, is a correct. So your grouping, this type of grouping is incorrect for the K map simplification. Another rule for a group can be only either horizontal or vertical. We cannot create group of diagonal or any other shape. So see that figure, this is suppose 1 1, it is some example for the 2 input K map structure. So this is possible, is a correct grouping, but this type of diagonal is incorrect. So that's the rule 4 for your K map simplification. Then rule 5, each group should be as large as possible. So which is the correct? In case maximum group combination is correct. So this is this method, this is the correct. So 1 1 1 1, in case this is one group and this is another group and this is another group. So suppose this two, this is the incorrect. So you always in K map simplifications, you understand the rule, all the rules, then only you are simplify the result. We are getting the least number of variables, least number of terms in the result. Okay. Then rule 6, opposite grouping and corner grouping are allowed. That is the example. This one type of important rule for K map simplifications. You see that one, what are the opposite grouping, that is folding type. So you see that one, this one, this one, this one, in case minterms are available in this 4 variable K map, this one, this one, this one, this one, this is the correct method. So folding this 2 and this 2, that is a, this suppose in separate your forming, it is not for incorrect one. In rule 3, there should be as few groups as possible. So the example of corner grouping is some examples and given. So okay, see that one. So what type of, at least some few groups as possible in case for using the K map method. So this is some solving according to the rule 1 to some rules, all the rules, some example for simplifications, the functions for the 4 variable K map. So this is one type of example. Here the sigma represents the sum of minterms. In case suppose SOP form, canonical sum of product form, canonical product of sum form. In case product of sum is where pi can be represents. Okay, so this 4 variable K map example. So 16 minterms. So this is the format for the forming the table. 4 variable, 4 input variables, 4 variable A, B, C, D. Then combination you see 4, that is 2 power, it may be 16 combination, that is 0 to 15. So starting 0 0 0 1, here 1 0 1 1, then 0 0 0 1 1 0 1 1. So that is minterms M0, M1, M2, M3, M4, M5, M6, M7, M8, M9, M10, M11, M12, M13, M14, M15. So this is the number of minterms for the 4 variable K map. So this is some example functions of here sigma 0, 8 means in K minterms 0 is you put substitute 1, then 8, M8 is substitute 1, then you simplify. You simplify, you are getting the answer for that one. Okay, so this is one type of minimize the Boolean function by using K map method. So finally, so first, what are the Boolean function, your simplification, just using the Boolean's theorem. Boolean's theorem mainly depending upon the some duality principles. You substitute Boolean algebra with the help of Boolean theorem, so Boolean algebra. And another K-map will be used again to simplify the minimize the Boolean function. Here in K-map we are not any Boolean theorem concept cannot be used. That is the major difference. So after that this we next topic will be designing for some combination logic circuits with the help of in case designing what type of designing concept. Then you first form the truth table, then you implementations after truth table you simplify with the help of the truth table, you simplify the what is the output expression. From that expression then you implementation by using some basic logic gates or universal gates or special function gates. So this is the summary for this week. So Boolean algebra and simplification of Boolean function with the help of Boolean algebra, and also minimize the Boolean function by using K-map method, 2 variable K-map, 3 variable K-map, 4 variable K-map. So finding the what is the results in canonical form of sum of product, canonical product of sum. Okay, so that's you always go through that given PPT or given slides. You always solve some more problem solving with the help of assignment and quiz. Then you will be easily understand. So in particularly this K-map you always solve more than problem. Then will be easily to understand. You once one or two times you read the rules for the solving the K-map, then you will be easily understand. So thank you very much for this summary points presentation. Thank you.